Let's talk about how to do transpose matrix transpose efficiently on GPUs using CUDA. The first method we'll be talking about is naive row method. I'll call this naive row method, where we load consecutive elements, um, consecutive threads, load consecutive elements row wise from the input matrix and store them column wise in the output matrix. So since adjacent threads, I show here that the green thread and red thread are adjacent threads. They access consecutive memory locations in the input data matrix. So we have a warp of 32 threads. So instead of while doing global memory loads, instead of there being 32 different global memory loads per warp, there'll be just a single global memory load per warp because of global memory coalescing while doing global memory load in this case. However, since green thread and red thread, which are consecutive thread locations, while storing into the global memory in the output matrix, they access different locations in memory. Like there is a stride of some um, like these many elements, there's a stride of these many elements, so they're not basically consecutive locations in the memory in the output array in the output matrix. So the global memory stores would not be coalesced. So in the problem with this naive row implementation is global memory stores are not coalesced. And in the second implementation, in the first implementation, we loaded row wise and stored column wise. In the second implementation, we would load column wise and store row wise. So here, although the global memory stores are coalesced, like consecutive threads access consecutive stored to consecutive data locations in memory, consecutive memory locations in the output matrix. Consecutive threads access non-consecutive data locations in the input matrix. So this is a problem where in this the problem is that global memory loads are not coalesced. And you can see that like if we do not use any intermediate structures, there will, because of the way matrix transpose is defined as an operation, there has to be either global memory loads that are not coalesced or global memory stores that are not coalesced. So in the code it looks like um, this is the ix, this is iy. So you can see this, we are loading by columns because if there are consecutive threads, one will have ix and one will have ix plus 1. So ix and ix plus 1 would have different columns, would load from different columns. Ix would load from here, ix plus 1 would load from here, but ix and ix plus 1 would store two consecutive columns in this case, in this naive column case. So how can we solve this? We can solve this by using an intermediate structure called shared memory. Intermediate, we store this in shared memory first. This is the input array matrix, this is the output matrix, and we store in shared memory. So for our discussion for now, let's assume that shared memory is big enough that it can store the entire input matrix completely. Okay, so let's first assume that it can store the entire input matrix completely. So we would load by rows, okay, and we basically we load this row into this column in the shared memory, and then while writing to global memory, we write also row wise. So once each thread stores its corresponding data in the transposed form into the shared memory, the shared memory is exactly what we want the output matrix to be. So we do a element wise copy from the shared memory to the output matrix, but note that we have to synchronize all the threads first because we want the shared memory to be completely ready before we copy it to the output matrix. So while copying to the output matrix, we copy row wise, load row wise from the shared memory, and store row wise into the output matrix. So let's take an example of a thread, how it, like where it goes. So this thread would um, would go here, right? Yeah, this thread goes, okay, this thread goes here in the shared memory, but this, I mean, this thread loads this data element from the global memory into this location, the shared memory, and this thread loads this data element from the shared memory and stores it into this location in the global memory. Okay. Um, so the code for this is, and this we, our discussion till now was assuming that the entire um, uh, input matrix can be stored in the shared memory. However, this is not the case, and we'll, to make our implementation work, we'll have to break the input matrix into grids, into blocks of tile size, and load each tile into the shared memory, transpose this, and okay, this is not a good example. Let's say we have, oh, okay, not a good example. What is a good example? Yeah, this. Let's say we, our blocks, these are the blocks, like this, these squares are represent blocks in our grid, and let's say we want to transpose this block. So we load this block into the shared memory first, and then all of these elements in the block would be mapped to these elements in the output matrix, right? This is the input matrix, this is the output matrix. So we do this block wise. So like this block has its shared memory and stores here. And similarly, each block has its own access to its own shared memory and does similar things. So the code is that for a given thread, let's say this thread, it has a given block ID x and a thread ID x. So we calculate the x this thread is responsible for, this x, and the y coordinate of the input, the x and y coordinate of the element this thread is responsible for. Then we, let's ignore this j component. Let's say just that j is 0 for sake of simplicity. J is 0. Okay, so in this first step, we store our each thread stores one data location from its corresponding xy location into the shared memory. Okay, and you note that we store row wise. Wait, we are loading from input data in a row wise fashion, and also we are, okay, so we are loading from shared memory, loading from global memory in a row wise, and storing into shared memory also row wise, loading from, so this code does these two operations, and this code uh, loads from shared memory in a column wise fashion. So you can see that this is column wise, right? Because consecutive threads, like threads with TID X and TID X plus 1, will load from the same column but different like rows in the same column. So we can see that the loads from shared memory are column wise, but stores into global memory are row wise. So thread ID TIDX is mapped to the data location X, TIDX plus 1 is mapped to data location X plus 1. So they are in the same row but different columns. So so yeah, this visualization is actually a little flawed. I mean, we can implement this in this way also. There's no problem with this, but the code is something like this, where this input tile is loaded. This row of the input dimension, this row of the input matrices tile is loaded into shared memory as is shared memory, and once the shared memory is all ready, because of sync threads, the shared memory is completely ready. We load from shared memory column wise and store row wise. Okay, but the problem with this is since we are loading from shared memory in a column wise fashion, consecutive threads. So let's say this thread, this thread was responsible for loading this element into this shared memory and loading from shared memory this location and storing into global memories this location. And the next thread here was responsible for these locations. So you can see that these two, when we load, when consecutive threads load from shared memory, since they are loading column wise, we get a bank conflict here, because the if the tile dimension is 32. Why do we get a bank conflict? Because the banks have size 32. So the way shared memory is stored in banks is, this is stored in bank number 1, this is stored in bank lane 2, this is stored in bank 3, this is stored in bank 31. This is stored again in bank 0, this is stored in bank 1, bank 2, bank 31. 0, 1, 2, bank 31. So if we pick up any column, this thread accesses this data location from the shared memory, and the next thread accesses this data location from the shared memory. But since both of these data locations belong to the same bank, we would need two, and let's say there are 32 threads in a warp. So to access, so 32 threads per warp will need 32 accesses to shared memory, because in a single access to shared memory we can get data from 32 banks simultaneously. However, all the 32 data elements that the 32 threads in the warp are accessing, they are in the same bank. 32. This is bank 2. In this case, this is bank 2. So since all the 32 threads are trying to access bank 2, they'll be serialized. So we'll have 32 independent accesses to shared memory because of the bank conflict, which is not optimal, and we want to somehow stop this from happening and get a situation which is sort of similar to this, where the same row has data in the banks 0, 1, 2, 31, such that when we are trying to access data when a warp is trying to access all of these data elements, it it can access all of these data elements to with a single access, with a single shared memory load, because each of these data elements belong to different banks. So in a single access to shared memory, this is bank 0, this is bank 1, this is bank 2, this is bank 31. In a single access to shared memory, it can get data from all of these banks. Okay. And the way we do this is nothing fancy. We just add a 1 here, which means that um, instead of the shared memory being perfectly 32 cross 32, it is now 32 cross 33. This is 32 and this is 1. And this is just dummy. Okay, we just work on the 32 cross 32 like region of shared memory. You can see, as you can see here, this code remains entirely the same. Actually, entire code remains entirely the same. However, now we won't have bank conflicts because of the way the data is stored in the shared memory. So I'm representing the banks to which these data uh, locations in the shared memory are mapped to. 31, and this should be 32, but I mean this is 0. Map to bank number 0, 2, 3, 4, 31, 0, 1. So you can see that in this column we have all banks from the 32 elements belong to bank 0, bank 1 up to bank 31, right? So in a single access to shared memory, we can get all of these elements, removing the bank conflict. So now there is no bank conflict. And this is the most optimized version out of all of the four versions we discussed till now.